Mechanical Engineering at Louisiana State University in Baton Rouge, and he's an expert in fabrication, replication, and of micro and especially nanostructures. Thank you.
Okay, thank you. Can you hear me? Okay, yeah. All right, so okay, I'm Sunggook Park. I'm from Louisiana State University, and actually, my expertise is nano manufacturing with the focus of nano imprint lithography. And recently, actually, I tried to expand my horizon towards nano injection molding. While I was working on mostly replication techniques, of course, replication requires what? Molds, right? So I think you have to use any available manufacturing technology to produce a mold insert, which is prerequisite for all the replication techniques. Okay, but since I'm working on micro and nano scale structures, actually also I'm very much involved in different micro and nano manufacturing techniques. So today, again, I will be focused on two things. So after a short introduction on these molding-based technologies, and I will mostly discuss on stem fabrication or mold fabrication by a focused ion beam milling. Okay, because the Matt already introduced some the prototyping tools to produce micro-scale molds. Okay, so I will mostly focus on how you can produce the molds with these nanoscale structures. Okay, and then probably after that we will have a short break, and then in the second part of my talk I will focus on two nanoscale replication techniques. So nano imprint lithography and nano injection molding. Okay, so now at LSU, okay, whenever I teach courses, I introduce myself like this. Okay, I'll show the next slide. So I will show this slide. Okay, when I teach any undergraduate courses, and I said, oh, actually, I'm a waffle maker. Okay, so actually the nano, when we are talking about nano, it sounds very formidable and it's difficult to produce, but it's really not the case. Okay, so all you need to understand. So that's the same when I first learned nano manufacturing or nano imprinted lithography. Okay, once you understand all the process of making waffles here, okay, then really you can solve a lot of problems associated with nano imprinted lithography or nano injection molding techniques. Okay, so now let's first think about how you make waffles. So I think you all know how you make waffles. Okay, so let me just briefly explain. What do you need first? What do you need first to make waffles? You need a waffle maker, right? This tool. Okay, and then what else you need? I think you need to make dough. You have to mix nicely with the right the combinations of the flours, water, and milk, or salt. And if you want to have some other taste, then you have to add something, right? And then now, what you need to do? You put this dough. You should have the right concentrations, right viscosity, and then you put into your mold. Then you close the mold, and then now you control the temperature mostly. I think it's wrong. I think first you have to increase the temperature, right? And then you put waffle, and then you close, and then after some time, basically your dough will be hardened, right? And then now what you need to do? You have to open it. But I think you will experience some problems many times. What problem? I think your waffle will be stick to the mold insert. Then to prevent that, what you need to do? spray, right? Spray. So you need to spray, okay? And then you may see another problem. So for some cases, I think you in the waffle maker, you have some cavities, right? But for some cases, your cavity is not completely filled. Or sometimes you put too much dough, and then basically it will go out of your waffle machine, and which makes your kitchen messy. So your mom will be very angry, right? So I think all of the things are, I think, associated with the issues that that can happen also in the real nanoimprinted lithography. And then also, if you don't control the temperature very well, okay, sometimes your waffle can be burnt, or sometimes it doesn't harden fast enough, okay? And then now, once you have waffle here, okay, then what do you need to do with this? I think you have to eat, right? This is the application for waffle. But in our application, we can use actually the replicated parts in many different applications. You have to really think about what you want to do with this, right? And then another issue is here, if you want to, so for the research, okay, if you want to do prototyping, or if you want to make a couple of samples, I think that's fine. But if you want to really commercialize, and you have to really consider like mass productions, right? So all of those things I think you have to consider. So as I mentioned here, I just summarized here. So there are a lot of issues you have to consider: materials and stamp, and then surface coating, spraying, right? And then tools, and also you have to optimize the process. And then if you also consider the rheology of the dough, spreading through the cavities of these tools, okay? So all of these things you have to consider for the real the imprinting replication process as well, okay? And again, finally, we are not only eating, but we have to think about all other applications. Mostly, we are working on biomedical applications. Okay, so this is the process scheme for nanoimprinted lithography, which is exactly the same as what I was shown in the before in the waffle manufacturing. So what do you need to do for nanoimprinted lithography? So the traditional nanoimprinted lithography, they used kind of silicon substrate, and then they put a thin polymer film on top of silicon wafer. Okay, but in our center, normally we are not really using silicon substrate, but we are just using the thermoplastic sheets. Okay, and then now what you need to do, basically you have to prepare the stamp mold. Okay, and then now you heat, okay, your substrate so that your polymer films, thermoplastics, okay, goes at a high temperature, okay, above is TG. TG is glass transition temperature. Okay, I will explain what TG is later, okay, in the second part of my talk. Okay, but simply if the temperature goes higher above this temperature, then what happens is the polymer becomes mobile. Okay, but it doesn't flow. It's not really kind of the melting temperature like water, but TG means your polymer chain becomes mobile. Okay, so now then what you need to do is you need to kind of apply force. Okay, bring the stamp towards your plastics. Then what happens? As you apply the force, I think the polymer will move and fill the cavities of your stem structures. Okay, so once your cavities are completely filled, then what you are doing is you cool down your system below TG. So simply you harden it. Okay, so now this is hardened. Now you separate your stamp from the molded plastics, and then now you have physical replica here. Okay, so this is the nano imprint process. the important aspects of nano imprint process is exactly the same as wafer manufacturing. Okay, or you have to think about resist, new materials, and then you have to produce stamps. Okay, depending on your applications, and also you have to think about the surface coating on the stamp surface just to decrease the adhesion. Okay, during this demolding process. And then also you have to control basically the what is that, the molecular weight, and then also the rheological properties of polymer, so that the polymer can easily fill into the cavities of micro and nanostructured surface stamped structures. Okay, and then also you have to control the temperature and pressure and time, and also you have to think about this the final application using the manufactured structures. Okay, so actually there are the moldings are there for a long time. It's not new at all. All right, so this is the example. This is a hot embossing machine, and this is the injection molding. And also in biomedical areas, a lot of people are using the PDMS casting. Okay, we are not saying this is high throughput production, but actually this is a very easy process and utilizing this replication techniques. Okay, and then also recently another high throughput manufacturing is a roll imprinting or roll to roll the pressing. Okay, but no matter what replication technique you want to use, okay, there's one important prerequisite, which is stamp or mold. Okay, we have to really produce stamp, which is the first prerequisites. Yeah, so the in the previous talk, Dr. Sopa already mentioned the DVD and Blu-ray disc. Okay, so basically replication, we use replication, for a long time, so it's not really new. Okay, but basically if you look at the CD and DVD, so actually this is basically the structures here for the CD, which is basically the microstructures. Okay, so the size of the pitch is around like 1.6 micron, and then the minimum structure is around some micron, it's close to 1 micron. Okay, but for the DVD, now the scale becomes even smaller, and for Blu-ray disc, actually this size of the pitch goes kind of sub 100 nanometers. Okay, but we could make such a structure very easily using injection molding. There are two reasons. The first one is it does not really, it's very low aspect ratio structures. Okay, the size looks very small. Okay, but the depth is so size is compared to the size, the depth is very small. Okay, so replication is pretty easy. And the second thing is actually it does not really require very accurate replication. Okay, so even though the size is a little bit different, actually it doesn't really it doesn't really harm the performance of CD or DVD or Blu-ray disc. Okay, so in such applications, I think again we already use injection molding, nanoscale injection molding. Okay, but okay, and then this is just a kind of summary of the small scale technology, right? So this is actually the scale here. So here we have a millimeter scale, here 1 micron and 1 nano. Okay, and then basically the Matt Hooper previously showed micro milling, so which is actually in this range. But again, I remember also we have a micro milling at LSU. Actually, the smallest structure we produced was around like 20 micrometer with micro milling, and then the optical lithography. Okay, depending on the wavelengths of the beam used, actually the smallest structure ranges from micron to like a sub-micron. Okay, and then basically E-beam lithography and focused ion beam, you can produce structure down to around 10 nanometers. Actually, with focused ion beam milling and e-beam lithography, there have been papers which shows that they produced the structures in the range of nanometers, like 2 nanometers, 3 nanometers. But actually, this is a very unusual case. And routinely, I think those techniques are used to produce structures in the range of tens of nanometers. Okay. And then Dr. Sopo mentioned the deep end lithography. So actually, which is one of the sharp tip based scanning probe microscope based lithography. And then again, that is also, you can produce structures below like 100 nanometers. Now, the question is, where are those replication techniques located? Okay, so for nano-imprinted lithography, basically, I think I will discuss later in the second part. It does not limit, there's no limitations, no practical limitations in terms of smallest structure that you can produce using replications. Okay, but again, the traditionally you can say we can produce structures, down to like 10 nanometers kind of routinely, but in our center we routinely produce structure even smaller than that as well. Okay, so now in the second part of my talk, I will try to focus on focused ion beam milling again, because there are two reasons. In the previous talk already, the Matt introduced how we can produce micro structures using micro milling. Okay, and for nanoscale mold, mostly people use either focused ion beam milling or e-beam lithography. Okay, however, I just don't want to introduce both of them because their optimization process are similar. So if you know one method well, then it's not difficult to apply a similar optimization process for the e-beam lithography. Okay, and the main reason is in our center we mostly use focused ion beam milling to produce nanoscale molds. Okay, so I'll focus on it, that part. Okay, so I showed the CD and DVD in the previous slides. Okay, so now one thing which differentiate actually the previous application of the CD and DVD is structures. So what nanoscale replication has been used mostly those are for optical applications, and for optical applications, their structures are mostly kind of periodic, regular structures. So that's relatively easy to make. Okay, but for our applications, if we want to really detect biomolecular which is in the range of 1 nanometers. Actually, in order to detect that, the regular structure doesn't work. Okay, we have to design a special nanofluidic structures, and this is one of the sensor structures that we are currently working. So basically, we have 2 in-plane nanopores. So I think it's easy to understand using this one. So basically, we have nanochannel here, and another nanochannel here, and there's another nanochannel here. Okay, and then actually between this nanochannel and this nanochannel, you have a very small dip, right? And then also you have between this nanochannel and this nanochannel, we have another small dip. So now just imagine that this is actually the structure that we make using focused ion beam milling. And then you put a cover plate on top of that. Okay, then now you can see we have nanochannel here, so enclosed nanochannel, enclosed nanochannel, enclosed nanochannel. But here you have a very, very small confined zone, and we call this as in-plane nanopores. Okay, So now what you can see here is this structure is not really periodic regular structures. Okay, so using conventional like a method like interference lithography, you cannot really produce this one. Okay, you have to have a special tools to produce, and then we use focused ion beam milling to produce such structures. Okay, and then actually this is kind of tilted view at these locations in plane nanopore. So basically, the depth of the in plane nanopore is around the 20 nanometers. Okay, and then after cover plate bonding, so after we replicate and cover plate bonding, actually we control this in plane pore size less than 10 nanometers. Okay, but the point is now how you can produce such structure which is not periodic, not regular. Okay, so for that we apply the focused ion beam milling. All right, so basically in LSU we have two different focused ion beam milling. Okay, so actually there are actually different depending on mainly depending on the ion sources used. Okay, so here we have gallium ion based focused ion beam milling. Here we have a xenon ion based the focused ion beam milling. Okay, and then basically depending on the ions used, basically the smallest structure you can produce are different. Okay, so for example, now actually gallium ion focused ion milling is kind of the most popular focused ion beam milling, and here the xenon the based focused ion beam milling, they have some pros and cons. Okay, but I will shortly introduce that. But what you can see here is for gallium ion of FIB, kind of the smallest structure you can produce is around 7 nanometers. So basically, this is the smallest beam size you can produce using this gallium-based focused ion FIB. And then while for xenon-based FIB, basically the smallest beam size is around like 20 nanometers. So you can just imagine, oh, okay, with this xenon-based FIB, you cannot really make small structures. Okay. However, you can mill very fast. I will just show shortly. Okay. So basically, because the xenon ions is large compared to the gallium ion, what does it mean? When you irradiate those ions on the surface, gallium ions, because it's small, it can penetrate into your substrate more easier compared to the xenon. Okay, in other words, because xenon cannot really penetrate it, all it can do is it can remove the substrate materials. Okay, so that's why normally for xenon-based FIB, the etching rate is higher, and then you can produce. You cannot really produce smaller structure, but you can produce the larger structure very fast. Okay, so in order to understand what parameters you have to control in order to produce the structure you want to build with FIB. Okay, I don't want to go into detail, but I think it's good to understand the basic structures of ion column. Okay, so it's a very complicated system. Okay, but if you see here, so basically you have here ion source. Okay, so basically ions, the liquid from the liquid ion, this gallium or xenon ions are produced here. Okay, and then basically you have extractor here. So basically you apply high voltage so that you kind of direct those produced ions towards the samples. Okay, so you simply apply a lot of high voltage here. Okay, and here you have aperture. Aperture is nothing more than a small hole. Okay, because we don't want to really have those ions beam, kind of spread. We just want to have focused beam. So we just put a small hole here. Okay, And then here we have lens, green ones. We have one lens, first lens, and the second lens, okay? So this is basically, it's not optical lens, it's an electromagnetic lens. Simply speaking, you just apply, because ions are positively charged, right? So you apply a certain voltage, negative voltage, so that you can either attract or you can repel, okay, those ions from this lens. So that the goal is you want to have really focused ion beam, okay? So here we have first lens, okay, and then here you have the octopore, okay? So another goal is, so in addition to have a smaller ion beam, so another goal is we want to have really symmetric ion beam. So if the beam becomes asymmetric, then basically the structure you produce will not what you wanted to get, okay? So basically using this octopore, you just adjust beam astigmatism, okay? And then now you have here, the blue one is a variable aperture. So you have, this is a small hole, okay? But you have a different sizes holes. So depending on the size of structure you want, you can change the size of this small hole, okay? So if you use a smallest hole, I think the final beam current is in the range of 1 picoamp. So if you want to make a very small structures, then you have to pick the smallest aperture. If you want to have a large structures, then it's better to use aperture with the higher the beam current, okay? And then now you have a kind of deflector and then also you have a lower octopore, which basically change the beam so that which allows the raster scanning the beam, okay? And then now you have okay, second range to have a final focus, and then you have sample here. So if you have this state of the art FIB, normally you can reach the focal size as small as 5 nanometers. And then the beam current is as few as like picoamps. Okay, but that is kind of optimized cases. And for the real cases, it's hard to get down to such a small beam size and then beam current level. Okay, so now when these ion beams collides into the substrate, what happens? Okay, so as I mentioned before, the one thing that happens is it removes substrate materials, okay? And this is a milling mode. And this is what we are using to produce structures, okay? But because ions are small, okay, some ions can be implanted into the substrates. It doesn't remove the materials, but it just stays there, okay? Which is not really good for our purpose, okay? But for some other applications, so for example, in the people working on semiconductors, they use this ion implantation to dope the semiconductor materials as they want. Okay, so they have a different application for this implantation mode. And then now, once you shine the ions into the substrate, of course, there are some reaction with the substrate, and then secondary electron will come out. Okay, and then basically, if you use like the secondary electron detector here, then you can do SEM, scanning electron microscope within focused ion beam milling machine. Okay, and that is basically the imaging mode. Okay, and then now, because the ion beam is a kind of high energy beam, if you kind of if you provide the certain gas precursor, okay, then you can initiate it kind of surface reactions on top of the substrate. So basically, you can deposit a certain materials, okay, locally and selectively. and this is the deposition mode. So I just show some example SEM images for each mode. So again, milling is what we are doing, and I will focus on in the next slides. And also we can do the imaging like SEM, but of course the resolution is even a little bit worse than the actual SEM, scanning electron microscope. Okay, and then basically you can also make like some nanostructures, basically sub-microstructures using this deposition mode in F5E. And then basically this is just simply the ion implantation using this the F5E. So there are 4 different basing functions with the ion beams. Okay, so there are a couple of parameters you want to control to produce the structure you want it to build. Okay, the first one is acceleration voltage. I just showed that once the ions are produced, then you have to apply a high voltage so that ions are directed towards the substrate. Okay, so of course this voltage determines how fast these ions are traveling toward the surface. Okay, large acceleration voltage will give more damage. Okay, but in terms of the milling mode, if you use like a low acceleration voltage, then basically the question is, can we make a smaller structure? The answer is no, because there will be some chromatic aberration effect. So the point is, normally we are not really controlling this acceleration voltage in F5E, and we normally standard acceleration voltage used is around 30 kilovolts. Okay, but what is really important is beam size and beam current and beam shape. I mentioned the aperture here, right? So we use kind of a different aperture to control the beam size and current, which is really important. Okay, so smaller beam size ultimately will make a smaller feature. Okay, but milling will take longer, and vice versa. So you have to control basically beam size and current depending on your needs for your structures to build. Okay, and beam shape is also important. Again, the goal is we want to have a smaller beam size, but symmetric beam size. Okay, and I think this is kind of misspelled. The astigmatization of the beam will produce distorted features. So actually, in the previous slides, we need to control basically the voltage applied to octopore to minimize this astigmatism of the beam. Okay, but in all, what you need to do in the real F5E, you need to mirror kind of a test part, okay, using a certain parameters, and you have in the kind of blank substrate, you need to do the test mirror, and then you have to determine what is the best shape and focus of your beam, and then now you have to apply the parameters for the real milling of your device. Okay, and also the milling mode affects your milling results a lot. Okay, so here actually it shows different milling mode you can choose. Okay, rectangular mode and line mode, polygon mode, bitmap mode, streamline files. But I think most people use either line mode or rectangular mode or bitmap mode. Okay, so I mean it's simple. Line mode means you raster scan the ion beam line by line. Okay, but for the rectangle, you define a certain rectangle. Okay, to raster scan. It's not a single line, but you define a certain rectangle for the milling. But for like 3D structures that I showed in the previous slide, normally we use a bitmap mode. Okay, in bitmap mode, you just you just draw your kind of 3D structures. Okay, using what is that? I forgot the name of the software used. Okay, so just a second. Okay, so basically you define the contrast. Okay, so depending on the depth of your structure to build, I think you define different contrast. Okay, in a bitmap mode, and then basically you load this bitmap file into FIB milling, and then basically you let the machine go, and then basically you have a different 3D structures by this FIB. Okay, so now the another important thing is parameters to control is the kind of dwell time and number of passes. So dwell time is simply how long the beam dwells in a single location before it moves to the next location. Okay, and then now, so I will show the effect of this the milling time in the next slides, and also the number of passes affects the milling results pretty severely. So even though here actually you mill actually the similar structures, okay, using different paths. So this, when you mill with a single pass, and when you mill multiple paths with a short dwell time, okay, you wanted to make a similar structures, but the results are completely different. So in general, if you use a single pass and then long dwell time, then what happens is you have a lot of redeposition. So when you did the FIB, you have the milling, and then you have a removal of material, but which will be redeposited on the surface. Okay, so that you cannot really have a very well-defined structures. Okay, so even though you want to have a very defined structure, because of redeposition, you have kind of smooth, like a tapered structures here. Okay, so in general, if you want to have more defined structures, it's better to use the multiple paths and with the short dwell time. Okay, so actually this is actually an example of how we mill using the bitmap mode. So this is a kind of exemplary like a bitmap structures. Okay, so so here basically the light contrast defines the depth, the deep structure, so the more milling, while the dark structure means we don't want to really mill. Okay, and then now so this is an example. So we wanted to make like an in-plane nanopore that I showed before, okay? And we just try to control the angles, okay, in this bitmap structure. So here, basically, we define the angle to be 50 degree, while here we define the angle to be like a 60 degree, and then we just try to mirror. And then what you can see here is when we define it doesn't really come exactly as we designed. So if you look at the angle formed here, it's not really 15 degree, okay? But what you can see is, so when you use the 15 degree, it's kind of very sharp, right? While when we use like 60 degree, then we have a structure like this, okay? So we have structure like this. Okay, so simply what it does is, by changing the bitmap design, basically you can modify the structure of your in-plane nanopore. Okay, so the another thing parameter we can use is basically milling time, as I mentioned before. Okay, so here, I mean, under the exactly same conditions and under the exactly same bitmap, okay, you just change the milling time. Okay, and then now after the milling, we just try to measure the in-plane nanopore width and in-plane nanopore depth. Okay, and then if you know the pore depth and pore width, then you can kind of calculate kind of equivalent circular diameter of this implant nanopore. And simply speaking, by controlling the FIB milling time, basically you can control the final dimensions of implant nanopore kind of accurately. So see here, depending on the time, you can produce like 25 nanometer all the way to like 50 nanometer the implant nanopore structures. Okay, and basically the smallest structure that we can routinely make FIB is around 10 nanometer, 15 nanometer to like 30 nanometers. This is what we make routinely using FIB. But you can make even smaller structures by modifying this FIB process. So which is called metal-assisted FIB milling. Okay, so all you need to do is before FIB, you just need to deposit a thin film of metals. Okay, and then now you do the FIB milling, and then the nature of the beam will produce kind of V-shape the cross-sectional structures. And then after milling, you remove the metals here, sacrificial metal, and then basically you can what you can have in your master mold is very, very, very small structures. Okay, so this was first demonstrated by the Ramsey group in 2010, and actually they showed the structures as small as 3 nanometers. Okay, using this metal-assisted FIB milling process. However, I have to mention that while they demonstrated the 3 nanometer FIB milled structures, they actually they did not really demonstrate kind of working nanofluidic devices. Okay, this is just to demonstrate the smallest structures. But actually, recently, we use actually similar structures and to demonstrate the working nanofluidic structures, and then the structure size is basically sub 10 nanometers. Okay, this is the last slide on this the focused ion beam milling. So now the one important side effect of this ion beam milling process is, as I mentioned, the ion implantation. Okay, so which is considered as kind of defect. So, but when and the degree of the defect strongly depends on what types of ions are used. So if you use basically this shows how the use of different ions, okay, affect the areas of ion implantation. So normally in this single crystal materials, they try to mill, and then they try to see how broad area your crystal becomes the amorphous because of this ion implantation. So when you use the same the acceleration voltage, you can see large amorphous area when you use gallium ion compared to the xenon ion. So what does it mean? This means if you in your applications, okay, this implantation or the damage of surface structure is a very big issue, then basically it's better not to use this gallium, but you can use actually the xenon. Okay, so depending on your application, you have to use you have to select different ion source to accommodate actually your device needs. Okay, so I think that's all for the first part of my talk.
We're going to take 10 minutes break and come back here for the imprinting.
Okay. Right. So in the first part, I just focused on stem fabrication by focused ion beam milling. Probably not all of you will actually work on this part, but for the second part is basically the core of this presentation and also the key technology for our center. So in order to understand the replication, the first thing is you need to understand the properties of polymers. Okay, so I mean, we are mostly focused on thermoplastics. Okay, so what if you at low temperature, if you try to think about like plastic bottles, okay, that's kind of brittle, still brittle, right? And then okay, polymer is kind of like a spaghetti chain. You have a polymer chain which are kind of entangled, right? Now you increase the temperature, okay, from then what happens? Now basically the polymer chain receives thermal energy, okay? But now when the temperature exceeds the first transition temperature, which is glass transition temperature, then now basically polymer chains are more flexible. But as I mentioned before, it doesn't mean that polymers will like really flow out. It stays as is, but once you apply kind of load, then it starts to deform. Okay, and then now if you increase the temperature further, then of course the molecular chain will repel each other, and then we will have a second transition temperature, which is the melting temperature. So now we know the melting temperature. So above the melting temperature, now the polymer becomes like a melt, like a watery. Of course, it's not really like a watery because the viscosity is high, but it can flow out. Okay, so now for nano imprint lithography, okay, normally we use the temperature above the glass transition temperature. Okay, so typically we use temperature around the 30 to 60 degree C higher than the TG of the polymers. Okay, so here basically this is a temperature range we use for nano imprint lithography or hot embossing. On the other hand, for injection molding, actually we use basically the viscous melt. So temperature higher than the melting temperature of the polymers. Okay, so keep this in mind. So now, basically the smallest structures you can produce using the replications, okay, can be determined using by using this radius of gyration of polymers. I will not go into detail, but now you can see here, okay, and basically that strongly depends on the molecular weight of the polymers. So when you try to calculate the radius of gyration of the polymers with two different polymer molecular weight, and then now you can see when we use 25K PMMA, okay, the radius of gyration is around 1.9 nanometers. And then when we use 950K PMMA, actually this is the PMMA molecular weight mostly used for E-beam lithography, okay? And then the radius of gyration is around 8.4 nanometers. And this is the polymer normally we can use for nano imprinting. And then you can see that actually you can really build nanostructures, okay? But how about even smaller than these nanometers? And theoretically, if you use the low molecular weight UV resin for UV nano imprint lithography, then basically there's no size limitation that you can produce using replication. So you can just look at here. So this is kind of replicated structures, okay, using UV imprinting, okay, using the low molecular UV resin. So now you can even clearly differentiate the height difference of 0.4 nanometers. So bottom line is, okay, if you choose the right materials, okay, then there's no limitations in terms of the smallest structures that you can produce using the molding. So actually, this is I showed the two videos here, okay? And this is the actual nano imprinting process that we are doing in my lab, okay? In the left, the video corresponds to thermal imprinting lithography. Okay, the right one corresponds to UV imprint lithography. So simply what you are doing is you have the okay, so let me just start again. And so you have basically your substrate, okay, and then you put your stamp on top of that. And then now in our case, we put very thin cover layer, and then now you apply the pressure, okay, and then after completely fill the complete filling, just we remove it and then we just manually separate the mold insert from the substrate. And this is actually the UV imprinting. So you put a drop of low viscosity UV, and then now you have substrate, and then you put you put stamps, okay? And then now you just press a little bit, and then now you put this entire assembly into our nano imprint machine, okay? Instead of applying high pressure, in this case, we apply low pressure and then we shine UV, okay, to cure, to make your polymer hardened. And then the separation process is the same. We just do it manually with hand. I think you will have KU has a similar machine, so basically you will have experience on that during this workshop. Okay, so I will just skip this one. So now, just to understand, because I'm still an engineer, so I still want to understand. I want to introduce some fundamentals of this the molding process. Okay, so actually so you can model this the imprinting process, okay, using fluid dynamics. So I will not introduce all the details, but here what you can see here is basically H0 is the thickness of polymers, and HR is the thickness of your stamp structure, okay, and then S, okay, basically S is the area of protruded area in your stamp, okay? And then under a certain assumptions, so the resin is incompressible, and then you have a quasi-stationary flow, and then this structure length is much larger than these lateral structures, okay? And then now viscosity is kind of constant, okay? Then you can apply this Navier-Stokes equation, and then you can finally calculate the time for the stamp to sink, okay? So which means the time to reach the complete filling of your polymers, thermoplastic, into the stamp cavities, okay? So simply this is how fast you can complete the molding. All right, so now let's think about what parameters are involved. Okay, so again, HF or H0 corresponds to basically the height of your plastics. Okay, but since we are using in most of our applications, we are using the bulk polymers. Actually, that is not very relevant. But now you can see now the sinking time is a function of viscosity. And S is geometry of your stamp, and then F is force. Of course, if you apply higher force, okay, then it will feel faster, right? The T will be short. Now, but also what you can see is this sinking time is related to geometry of your stamp structures, L and S, okay? So now, just think about these two different cases. Okay, so now the first case, you have a stamp with a single small structures in the center. While the second case, you have many structures here. And you have the same thermoplastic substrate. So which one? So and if you imprint under the exactly same condition, so which one will complete imprinting faster? 1 and 2. So 1, raise your hand. 2, raise your hand. Okay, I think most of them, yeah, did the right things. So now, when I started imprinting, I thought probably this will feel faster because you have only small structures to fill, right? But which is not the case. If you look at this formula, okay, so S is basically the area of protrusion. So this means that this area corresponds to S. So you have a larger S while when you have like the multiple structures, right? Then you have a small S. So just using this rheological formula, you can see that it takes way, way longer to fill actually this structure compared to this one. Okay, actually, theoretically, the reason is in order to fill these structures, the polymer should flow from all over the surface, squeezed into this small area. While if you have multiple structures, then basically polymer needs to flow only small distance to fill into the cavities. Okay, and then basically this formula actually captures actually this phenomenon. So again, this is better than this one. So when you design your stamp to fill easier, I think it's better to. So if you don't, even though you don't need many structures, just for the better filling, it's better to put some dummy structures around your key structures to enhance the fast molding. Okay, so basically the first rule to determine stamp geometry is you want to keep the distance of lateral flow as small as possible. Okay, and as I mentioned, to prevent large features surrounded by a large unstructured area, which is bad. Okay, or you want to distribute patterns over the whole area if possible. And even though you don't need, it's a good idea to add some auxiliary structures to enhance kind of rheology for during the molding process. Okay, now, so we discussed about molding. How about demolding? So demolding is the process to separate, right? So if you have a strong adhesion, then what happens? Like a waffle manufacturing process, if you have a strong adhesion, then waffle will stick, all right? And then you have defects. You don't want to really sell such a ugly waffle to your customers. The same thing for our NIL. So this is kind of the most basic formula for adhesion that I can find from this physics, the papers, okay? So adhesion is a function of, this is kind of a surface energy. In other words, work of adhesion, but it's basically surface energy, okay? And K is composite Young's modulus. So simply how hard your material is, your substrate and stem material is. Okay, and then R is basically contact area. So R is simply determined by your stamp design. Now, the question is how you can lower the adhesion. In other words, how you can improve demolding. Okay, so again, there are three strategies you can come up with. First one is you want to lower the surface energy. Okay, or you want to lower the Young's modulus, or you want to lower the contact area. How you can do that? Again, as I mentioned, the contact area you can control by stamp design, and normally to lower the Young's surface tension, we put spray, right? Spray, and we do the exactly same thing in the nano-imprinted lithography, and we call this anti-adhesive coating layer. Okay, so basically you coat your mold surface to have a kind of low surface energy. Okay, to control the surface energy, to lower the surface energy. Okay, now another thing which people mostly neglect is kind of lower the Young's modulus of mold or resist to improve kind of demolding. So as I mentioned before, instead of using spray in nano-imprinted lithography, we use anti-adhesion surface coating to lower the surface energy on the stem surface. Okay, and this is kind of the typical the molecule self-assembled monolayer molecule that we use, and then basically we use actually the vacuum deposition. Again, if you have nanoscale structures and if you dip into the liquid phase, then because of surface tension of the water or solutions, then you don't have really homogeneous surface coating. So normally in the nanoscale stamp anti-sticking, anti-adhesive coating, we prefer kind of wafer phase. Okay, so it just shows the contact angle before and after this this silane coating on the silicon surface. Okay, and then as I mentioned, another way to control is to kind of lower the Young's modulus of mold or resist. Okay, so in our lab, okay, so this is basically the SM image of the silicon master mold, which we produce using focused ion beam milling that I showed before. Okay, but normally we are not using this as a stamp for nano imprinting. Okay, and instead what we are doing is we replicate this structure into another UV resin. Okay, and normal UV resin is also the kind of polymers, so it has a lower surface, low Young's modulus. Then now we use this replicated UV resin mold to thermal or UV imprint the final device. Okay, and then that works perfectly. And that, okay, utilizes the principle that I just showed, okay, to lower the surface adhesion by using low Young's modulus material. Okay, and another important thing in the thermal nano imprinting is to control the demolding temperature. Okay, so simply speaking, I think we just using the exactly same structures, we just try to measure the demolding temperature at different, demolding force at different demolding temperature, and then now you can see that there's some minimum here. Okay, so simply speaking. Okay, there is a competition between adhesion and thermal stress. So when you do the imprint and then cool down, okay, as you cool down, thermal stress builds up. So if you cool down too much, then thermal stress becomes very high. But if you don't cool down, and if you are at an elevated temperature, then basically adhesion plays a significant role. Simply speaking, it's a sticky, so when plastic becomes a little bit elevated, then if you just try to push, then it becomes sticky, right? So it is competition between adhesion and thermal stress, and then normally there is a kind of optimum the temperature for the demolding. So that is particularly important for the thermal imprinting. So normally I strongly suggest that, okay, when you do the demolding, so do the demolding slightly lower than TG of the polymers. So in this case, basically we use the PMMA whose TG is around 110 degrees C. Okay, when the demolding temperature is close to the TG, then demolding force is even increased again. So around 30 degree, 40 degrees C below TG, maybe a good temperature for the demolding temperature. I will skip this. Okay, so now the very, very important thing, okay, if you are to work on nano imprinted lithography, nanoscale any the devices, keep your stamps clean. I think most of you are in chemistry, right? I'm in mechanical engineering. What I hate in mechanical engineering is they don't have any idea about the importance of cleanliness. Because if you go to the mechanical engineering machine shop, it's a little dirty, it's bulky, right? So when they come here, they work like that. Then after you work with the surface, with your specimen, and then now you imprint results are bad. That is fine. But you know what is worse? If you have some dust particles or contaminations, then it will damage your expensive stamps. The resin stamp is okay because this kind of replication, but if your silicon stamps was kind of damaged, then that make me really mad because it's so precious and so time consuming to make a stamp. So when you are to work in nanoscale things, please keep clean. It's very, very important. Okay, so Yeah, I just try to focus on some important technical aspects if you want to really work on nanoimprinted lithography. And then now let's move to the injection molding. Okay, that is very similar. Okay, but instead of using the temperature above the TG, so for injection molding, we use the temperature higher than melting temperature. Okay, so we are using polymer melt. So this is actually basically the schematic structure of injection molding. So you have a hopper here, and then here you put the plastic granules. Okay, and then here you have a screws, and then around the screws you have a heater. So what you are doing is you kind of so because of the heater, I think the plastic granules will become melt. Okay, while this molten plastic will be pushed. This molten plastic will be pushed towards these directions using this screw. Okay, and then now here you have kind of mold and mold cavities. So simply the goal is you want to fill these mold cavities between two parallel platens. Okay, through these small holes. Okay, so that is basically the injection molding process. Oops. So this is the video which I got from KU. I think you will see this machine and you will work on this machine probably tomorrow. I don't know, today or tomorrow. Okay, so compared to the nano imprinted lithography, injection molding is really, really fast. Okay. Okay, I think it's too loud. So for the nano imprinted lithography, okay, normally the kind of the process time for each batch is around like 15 minutes, or if you have a very complicated and large structures to fill, then sometimes it takes like 30 minutes. What in average you say between the 10 to like 30 minutes. But as you have seen here, injection molding, that because you use basically polymer melt, okay, you can push this melt into the mold cavities very fast. Okay, so the kind of process time is between like several seconds, and even for the complicated structure, it's like one or 2 minutes. So compared to nano imprinted lithography, so nano imprinted lithography can be considered as a high throughput manufacturing process, but for us, this is still kind of intermediate step, the technology. But ultimately for commercialization, you have to go either towards this nano injection molding or the roll-to-roll process. Okay, so there are parameters to control to have this good nanoscale injection molding. I will not really go through all the details, but I just want to list here because in case you need it, you can just go back to this slide and then check each parameters. Okay, so injection volume, clamping pressure, and resin temperature, and injection pressure, injection speed, injection time, and mold temperature. But actually, among them, the most important thing is basically injection unit control, injection volume, and then mold temperature. Okay, and the resin temperature, I have to note that this resin temperature and mold temperature are different. Resin temperature is basically the temperature of the resin, so which should be in the higher than the melting temperature of this polymer, while the mold temperature is the temperature. So the mold temperature is basically temperature at the mold surface here. Okay, so that is slightly different. So those are kind of the example of the nano injection molding of the in-plane nanopore sensors that I showed. So actually that was this work was done at KU. Okay, so this is kind of the silicon stem structures, and this is kind of high resolution AFM image for injection molded cycloolefin polymer COP. Okay, you can really see that you have a very small constriction within this two connecting nanochannels. Okay, so again, this is we call the in-plane nanopore. And that is another example of injection molded device here. So basically this is the X-TOF device. Okay, so yeah, I think you can see this is very well replicated. Okay, so basically what we tried to do was we tried to compare the injection molding and nanoimprint lithography in terms of replication fidelity. So which one do you think is better? So actually, I gave a kind of invited talk at this EIPBN conference, which is kind of one of the major conference for micro nano processing. And most of them think, so nano imprint lithography may have the better resolutions compared to the injection molding, because injection molding is a kind of a more high throughput process and it's kind of more bulky devices. Okay, but basically what we tried to do was using the exactly same stamp. Okay, we tried to make a device using injection molding and nano imprint lithography. Okay, and then now we put the cover plate on this nanofluidic device, and then we filled electrolyte into these fluidic structures, and then we measure the current. So basically, this current indicates the size of the smallest structures in this nanofluidic vials. Okay, so now all you need to see is the variation of those current. Okay, so basically, this is average is similar, even no matter whether the devices are made by injection molding or nanoimprint lithography. But what surprised us was you can see the standard deviation or relative standard deviations. Okay, so for the injection molded device, the relative standard deviation, so basically, which indicates device to device variation, is lower than the device variation produced by nanoimprint lithography. So I was also very surprised when I saw this, and I was happy. Okay, and then after I thought why it happened, actually, our interpretation is, as you have seen before, for nanoimprint lithography, how we do the demolding. After molding, we just try to separate manually by hand. We are not doing like this. We are doing very carefully, okay, but still it's a manual. So this means during the demolding process, there can be some additional deformation, okay, occurring in the nanostructures. Again, these nanostructures, okay? So slight deformation will show up in this variation. But for nano injection molding, as you have seen this, basically, after molding, okay, when you separate these two platens, the molded part is separated automatically. Okay, so basically it's like automatic demolding, and which will kind of lead to kind of less device to device the variation. So basically initially we were very concerned whether nano injection molding will have a better so may have some issue with the device to device variation, but finally what we found was injection molding is really better, okay, to obtain the device to device uniformity. Okay, so actually the focus of my talk today is, okay, so basically nano molding, both nano imprint lithography and nano injection molding are very, very simple, easy technologies for you to use for your application to produce micro and nano structures. Okay, and then basically there are a lot of things to control, but just think about wafer fabrication. Then you should be able to solve a lot of problems that you may have during developing this technology for your applications. I think that's all I have today. Thank you.
Thank
for
you, Sunggook.